Hi, Assalamualaikum, and a very good morning to Dr. Sharifah Zurina and all my fellow friends. I am the representative of Group 9 to present about Second Order Differential Equation application. My name is Umaira Azhara binti Zaidi, and my group members are Muhammad Amirul Ashraf, Muhammad Takif Iman, Nur Dayana Natasha Muhammad Johan, and Aswat Shahrin Shabasa. The table of content of this presentation, starting with introduction, and then proceed with problem statement, methodology, result and discussion, conclusion, and finally references. Now, let's start with introduction. Second order differential equation serve as a special topic for our study. We study because of the special interest one can have in the physical situation that these differential equations are modeling. We study several cases of the motion of a single weight hanging from a spring, which are where the motion is free, where the motion is damped, and when there is a forcing function present. F equals to ma is Newton's second law of motion, where m is the mass of the moving object and is its acceleration. When the spring is hanging vertically, there is an additional force on the mass that due to the gravity. Assume that a massless spring's natural duration is angle, and then when an object of mass m is suspended from the spring's end, the spring extends the unit and is in equilibrium. My double prime plus by prime plus ky equals to rt. Based on the equation above, there are a few cases depending on the b and rt value, which is undamped oscillation is b equals to 0, damped oscillation is b is not equals to 0, free oscillation is rt equals to 0, and forced oscillation is rt not equals to 0. Now we reach the problem statement, which is question number 9 in tutorial 2.1. A vibrating string with damping can be modeled by a differential equation my double prime plus by prime plus ky equals to 0. The first question is, based on the equation above, find if m equals to 10, k equals to 250, b equals to 60, y equals to 0.3, and y prime equals to negative 0.1. Find the equation of motion for this system. And the second question is, find the frequency of the oscillation. And the last question is, we need to compare the result of this problem to question 8 and determine what effect the damping has on the frequency of oscillation. What other effects does it have on the solution? Now, let's move to methodology. The vibration has two types, which is homogeneous and non-homogeneous. But in this particular problem, we are going to focus on homogeneous second-order differential equation. This is because the string vibrated with damping that can be modeled by a differential equation my double prime plus by prime plus ky equals to 0. This homogeneous equation can be further break down into two more categories, which is damped and undamped. In this case, we found that the solution leads to undamped because alpha is less than beta. Hence, b squared is less than 4mk is the indicator for undamped. Therefore, we have to use the equation yt equals to exponent to the power of alpha t times k1 cos beta t plus k2 sin beta t. Then, we can use the boundary given, which is y equals to 0.3, t equals to 0 to find the k1. The next step is we have to differentiate the yt using power rule. After that, substitute with y prime equals to negative 0.1, t equals to 0. And we will get the general equation yt equals to exponent to the power of negative 3t times 0.3 cos 4t plus 0.2 sin 4t. Now, let's focus on manual calculation of A. Given the constant value is m equals to 10, k equals to 250, b equals to 60, y equals to 0.3, and y prime equals to negative 0.1. we need to substitute all the constant value into this equation to find the value of m. So we get the value of m, which is m equals to -3 plus minus 4i. As we know, alpha is equals to -3 and beta is equals to 4. Now we can see it is underdamped. If it is underdamped, we need to use this equation as general equation. Next, we need to substitute the value of y and the value of t into the general equation to get the value of k1, which is k1 is equals to 0.3. After that, we need to find the equation of y prime using the product rule. After we get the y prime equation, we need to substitute the value of y prime equals to -0.1 and t equals to 0 to get the value of k2. After we get the value of k1 and k2, we can substitute it back into the general equation, which is yt equals to exponent to the power of 3t times 0.3 cos 4t plus 0.2 sin 4t. For question B, we need to find the value of frequency. As you can see, our general equation is this one, and we can express it to be like this. And we know the value of beta is 4. Beta is equals to 2.2 pi f, which means 4 equals to 2 pi f. And that frequency is equal 4 over 2 pi hertz. Answer for C is, as we can see, question 8 is a mechanical system for case 1. Underdamped free vibration, which is P equals to 0. But for question 9, it is mechanical system case 2. Damped free vibration, which is B is not equals to 0. For that, when m equals to alpha plus minus beta, it is related to the roots p squared less than 4mk, which is underdamped or oscillatory motion. The solution is an exponential factor or known as a damping factor. For the result and discussion, we can substitute the variable value of t into the general equation to get the value of motion. When we use the graph application, we can get the oscillatory graph, which accurately same with the undamped motion graph. Now we reach the final part, which is conclusion. Second order linear differential equations are used to model many situations in physics and engineering. As explained in this chapter's introduction, the additional physics concept in this case is divided into two categories, which is the nature of how the string is excited and minor correction or addition to the wave equation. When we have a situation of mechanical system as problem statement, the most suitable case is case 2, which is underdamped, b squared less than 4mk. Underdamped is a condition in which damping of an oscillator causes it to return to the equilibrium with the amplitude gradually decreasing to 0. The system returns to equilibrium faster but overshoots and crosses the equilibrium position one or more times. The sine and cosine terms in the solution cause underdamped system to oscillate. However, the exponential term eventually takes over and the amplitude of the oscillation decreases over time. In conclusion, the second order differential equation can be used for the resolution of this question, especially in linear homogeneous equation, which is one of the best way to derive and solve the problem. This is the references to complete our task. That's all from me. Thank you.